lot of chemical processes, most of them, occur between particles. And so it's two of this particle interacting with one of that particle. It's on a particle-to-particle basis. And so sometimes we need to know how many particles are in this sample. We can't count them because they're too small. So we count them by weighing them. This is a lot like you would go to the hardware store and need some nails. And this would be like the corner hardware store, the old-fashioned one, where they've just got this big old bin of nails. You're not going to count the nails. You need 2,000 nails. You're not going to count them. You're going to weigh them. They've got a big scoop, and you put the nails in a balance or a scale, and there's some little sign there that tells you how many nails are in a pound. And so you can count the nails by weighing them. And that's what we do with atoms. They're too small to count, and so we count them by weighing. We use units that are counting units for several different types of things in everyday life. One of these units is the dozen. A dozen objects is 12 objects. It doesn't matter what the object is. You can have a dozen donuts, you can have a dozen pencils, you can have a dozen cars, you could have a dozen planets, right? Dozen means 12 things. A gross is a dozen. So it's 144 objects. Usually these are smaller things, like a gross of vials. But if you're a big organization, you might buy a gross of pencils at a time, 144 pencils. Well, in science and chemistry, we have our own unit for counting because even a gross is too small of a number. We use what's called the mole, M-O-L-E. And it's abbreviated MOL. Personally, I don't think it's a long enough word that it really needs an abbreviation, but it has an abbreviation. So we sometimes call this the chemist's dozen because it's a counting number. And instead of 12, it's this number, 6.02214 times 10 to the 23rd particles or objects. And that number is called Avogadro's number in honor of the scientist whose work led to the determination of this number. So if we talk about a mole, we mean 6 times 10 to the 23rd particles. This is a number that you need to memorize. You should learn it to at least 4 significant figures, 6.022 times 10 to the 23rd. It's actually known more accurately than that, but most of our other measurements would limit it, so we don't need to worry about it. You can specify Avogadro's number of anything. You can have Avogadro's number of marbles. 1 mole of marbles is 6.02214 times 10 to the 23rd marbles. You could have a mole of sand grains, 6.022 times 10 to the 23rd sand grains. This is a very big number. A mole of marbles, if I remember correctly, would cover the Earth to a depth of, I think, a mile or something ridiculous. That's a lot of marbles. That's a lot of marbles. So a mole of anything is this number of that thing. Mole is a unit that some students have a hard time getting their brain around. And you might have gotten through your previous chemistry class successfully and still just didn't quite get this whole mole thing that we keep talking about. The mole is really, really important, and we use it a lot. How did the mole get its specific value? The unit mole was set up to make things more convenient. So the mole, the value of it is equal to the number of atoms in exactly 12 grams of pure carbon-12. We heard about carbon-12 before. Carbon-12 has 6 protons and 6 neutrons and was used as the definition of the atomic mass unit. One atomic mass unit was 1/12 the mass of this carbon-12 atom. And now we're saying that the mole is the number of atoms in 12 grams of carbon-12. What that means is that 1 mole of carbon atoms weighs 12 grams. How much does 1 atom weigh in atomic mass units? One carbon atom, not a mole of carbon atoms, but 1 carbon atom, how many atomic mass units? 12. 1 atomic mass unit is 1/12 the mass of carbon-12. 1 carbon atom is 12 atomic mass units. 1 mole is 12 grams. So it was set up so that the numbers would be the same. 1 atom is this amount of atomic mass units. 1 mole is the same number, but in grams. Converting with moles and numbers of atoms is a lot like converting with eggs and dozens, but you're going to use a different number instead of 12. So 1 mole of atoms is Avogadro's number of atoms, and so you can make 2 conversion factors, and you just put them in so the units work out, and it's dimensional analysis, and everybody's happy. This is a number, though, that you have to use scientific notation on your calculator, because I haven't seen a pocket calculator that has enough decimal places on its screen that you can enter all those zeros, and who would want to count them out anyway? So make sure to do the calculations along with me, because there's a lot of common errors that students make with scientific notation, and it's best to get those taken care of right now. A pure silver ring contains 2.80 times 10 to the 12 silver atoms. How many moles of silver atoms does it contain? Okay, well, let's write down the number, 2.80 times 10 to the 22 silver atoms. And the question is, how many moles? Well, if I said I had 36 eggs and wanted to know how many dozen, could you do that? Sure. Because you're familiar with eggs and dozens, right? Same idea, though. The relationship between atoms and moles is 1 mole equals 6.022 times 10 to the 23rd atoms. So we can take this number of atoms and convert directly to moles. And I want moles on top, and I want atoms on the bottom. So the units work out. And then I look at my conversion factor. 1 mole is this number of atoms. You'd never say that 1 egg is 12 dozen eggs, would you? That's kind of ridiculous. But students switch these numbers sometimes. It's 1 mole and Avogadro's number of atoms. So, get out your calculator. 2.8 EE22 divided by 6.022 EE23, 0.04649619, no, that's an 8 moles. How many sig figs should it have? 3. Avogadro's number is not an exact number. I wrote it here with 4 significant figures, but this number only has 3. We don't want our constants like this to limit our significant figures in our answer, and usually they don't. So this is 3, this one's 4. So I should have 3 sig figs, 0.046, and I have to round up. 0.0465 moles. Any questions? If you got a really, really big number, you have a scientific notation issue with your calculator. And we can fix that during lab. Questions?
Can I ask a question on this during the lab instead of
Uh-huh.
right now? So
Absolutely.
so we can finish
Yeah.
the lecture?
Yeah, because we do need to finish, don't we? It was very late. So to count the atoms by weighing them, we need one more thing. We need the mass of a mole of atoms. And that the mass of a mole is called the molar mass. The atomic mass is the mass of an atom. The molar mass is the mass of a mole. And because of how the mole was defined, an element's molar mass in grams per mole is numerically equal to the element's atomic mass in atomic mass units. And somehow in the slides, I think what was a piece of information that should have been stated, on the periodic table, those numbers below the element symbols, those are the average atomic masses for the naturally occurring isotopes. So if we look at carbon, and that periodic table says 12.0108, that's the average mass of a carbon atom in atomic mass units. That's the mass in grams of a mole of carbon atoms. 26.98 grams of aluminum is equal to 1 mole of aluminum. If we look up aluminum on here, 26.98. That many grams is equal to 1 mole. 1 mole is Avogadro's number of aluminum atoms. There's carbon, 12.01 grams is 1 mole. That's the same number of atoms. Helium is very light, 4.003 grams in 1 mole. And that's equal to Avogadro's number of helium atoms. The lighter the atom, the less mass you have when you have the same number of them. A dozen medium eggs are going to weigh less than a dozen jumbo eggs, right? Because the jumbo eggs are bigger. And so if you have 12 of each, the bigger ones are going to weigh more. So we can convert between mass and moles using that molar mass. And we get these numbers off the periodic table. So we look at the periodic table, and under carbon it says 12.01. 12.01 grams equals 1 mole. We can make that into 2 different conversion factors, grams per mole or moles per gram, whichever we need for our equation. Let's do an example. Calculate the amount of copper in moles in a 35.8 gram pure copper sheet. I read the words. I'm going to take the number, 35.8 grams of copper. And what do they want to know?
Moles.
Amount in moles. Well, I can convert grams directly to moles. The relationship is found on the periodic table. We find copper, and that periodic table says 63.546 grams of copper is equal to 1 mole of copper. So that's the conversion factor I use. 35.8 grams. That's not a G. And then I want moles here and grams on the bottom. The units tell me whether I'm going to multiply or divide. I don't have to remember. 1 mole is this many grams. 1 mole, 63.546. So I've got 35.8 divided by 63.546. How many significant figures should that have? 3. This has 3 sig figs. This has 5. Now, depending on what periodic table you're looking at, you might have one that's 4 or more. The number might be slightly different because as we learn more, we're updating the periodic tables. Use the one that you have. You do not want to round this. You don't want to write 64 down here for your molar mass of copper. You want to use whatever's on your periodic table. So 3 sig figs would be here, so 0.563 moles. Any questions? Yes?
The one that you gave us and the one up there, are they the same masses or do they differ?
I'm guessing they're slightly different. This one's pretty new. It was put up over Christmas break. On a test, I'll give you a periodic table, use that one, and you'll be good. If you came up with an answer that was different by 1 in that last digit, Mastering Chemistry shouldn't have an issue with that. So this part's just really going over how to work out the plan for doing some of these calculations. It's really just unit conversions. To count the number of atoms, we're going to find the mass of it. You can convert the mass to moles using the element's molar mass, and then you can convert moles to number of atoms using Avogadro's number. Let's do an example. How many carbon atoms in a 1.3 carat diamond? And then it's telling us diamonds are a form of pure carbon, and 1 carat equals 0.20 grams. Well, let's write down the numbers. I've got 1.3 carats, and I'm told that 1 carat equals 0.20 grams. And what am I trying to find? Number of atoms. So we got 2 different things here that we could potentially start with. I want to start with the one on top because that's just a single unit. This is an equality, and I could use that as a conversion factor. So I could go from carats to grams using this information that they gave me. And from grams, I could do what? I could go to moles. And then from moles to atoms. It's not the only way, but just following what they did in the book. 1.3 carats. Got grams and moles and atoms. Carats, grams, moles, atoms. And then fill the units in the bottom. And make sure that they actually cancel out, and not just that you wish they canceled out. One carat equals 0.20 grams. They gave that to us because that's a weird conversion factor that nobody remembers. So 1 carat, 0.20 grams. How about this moles and grams thing? Where do we get the numbers for that? Periodic table. This is carbon. We need to know that carbon is C, and under C, we have 1 mole is equal to 12.0108 grams. And then we need the number relating atoms and moles. This is the chemist's dozen. Mole is like the dozen, and atoms is like the eggs. So the number goes with the atoms. And I always forget to leave enough room for that.
You did the 12.0108 because that's carbon, right?
Because it's carbon. And I was using the periodic table on the wall. What I usually do is, a lot of these I have 4 sig figs memorized, and so I would normally just do 12.01. 1.3 times 0.2 divided by 12.0108 times 6.022 EE23. And how many sig figs should this have? 2. This is our final answer. I'm going to round it right now. 1.3 times 10 to the 22 atoms. That's really, really big. Is it okay that it's that big? So a 1.3 carat diamond, can you see that with your eyes? Yeah, that's a nice sized diamond. That's pretty big. There's got to be a lot of atoms in it, right? So it has to be a big number. Yes?
Does it matter how many significant figures we put for the weights of elements?
That's a good question. Does it matter how many significant figures I put in here? It does and it doesn't. In this calculation, I have this number with 2 sig figs and this number with 2 significant figures. I do not want to have my molar mass limit the number of significant figures. We also don't want to introduce rounding errors. So what I would say is you want to use at least 4 significant figures in your molar mass. So if you want to do 12.01, that's fine. Carbon is really close to 12, and so if you rounded it to 12, it probably wouldn't cause a problem. But things like chlorine, if you round that to the nearest whole number, that's going to cause a problem. So don't get into the habit of rounding your molar masses to whole numbers. It's not a good idea. I'm going to skip that one because I'm tired.